Okay, we're gonna go off to chapter 13, which is gases. So when we're talking about gases, obviously we are talking about the state of matter where everybody has completely broken away from one another. They are flying around in the container, and as they're flying around, they are causing collisions. And as we see, the number of collisions will definitely have an impact on pressure. And basically, as the collisions will increase, we would expect the increase in pressure to occur. As the number of collisions sort of decreases, we would expect the pressure to decrease as well. So, um, a lot of sort of the gas laws we talk about has to do with whether or not you're sort of increasing the collisions that are occurring or decreasing the collisions that are occurring. So let's start talking about some of the substances that under normal conditions can exist as gases. When we kind of talk about normal conditions, that's sort of everyday conditions, kind of room temperature sort of conditions. That's a pressure of 1 atmosphere. So an ATM is a unit of atmosphere. And 25 degrees Celsius is sort of a normal sort of room temperature. And under these sort of normal sort of conditions, everyday conditions, when we have something that's an ionic compound, which is a metal and a non-metal together, obviously held together by the opposite attraction of the charges of the ions, so our positive ion and our negative ion, that is held together by those really strong electrostatic attraction. And because of that, under normal conditions, an ionic compound really will not go into the gas phase. So if you think of like a salt or something like that, it's usually, for a lot of the cases, a solid is typically what we find sort of something, say like sodium chloride or something of that nature. And they're held together in sort of their ionic compound by these really, really strong sort of intramolecular forces. And to get him to sort of go into the gas phase, it would have to sort of overcome these forces, and a lot of energy would have to be supplied to it. And that typically doesn't happen under normal conditions. You could kind of heat the heck out of an ionic solid and stuff like that. Thank you. And it will really just start to melt rather than sort of just go into the gas phase. So it'll just keep melting before it kind of does the gas phase. So ionic compounds typically are not gases because just by the nature of how they are held together by those forces, which is a really strong force, they again are not allowed to sort of go into the gas phase. And that's a little bit different than what we see with molecular compounds. Now, molecular compounds, on the other hand, are obviously guys that are going to be sharing electrons. So some type of covalent bonding is basically happening here. And different than that, there are a lot of molecular compounds that are just gases under normal conditions. So things like carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane, CH4 there, which is kind of what comes out when you light your Bunsen burner, for example, in lab. These are gases under normal conditions. But even molecular compounds themselves, under a lot of normal conditions, are actually not gases. A lot of them are liquids and solids. The main difference, though, between, say, a molecular compound and an ionic compound is they definitely can be a lot of times converted into a gas much easier than, say, an ionic compound. And if we just take a common example that we're all familiar with, and that is water. And water, for example, in the liquid phase is held together by what are known as intermolecular forces. Water is a polar molecule, as we talked about with bonding. The oxygen is more negative, hydrogen side there is more positive. So they are held together by this sort of opposite attraction between that one water molecule and another water molecule. The negative side of one will be attracted to the positive side of another. That is actually specifically known here as hydrogen bonding because it involves a hydrogen. And hydrogen bonding is a type of intermolecular force. And an intermolecular force is the force that holds this entire molecule together with this entire molecule. So that's the force that holds those two entire molecules basically together with them. And obviously, in, say, liquid water, there's lots and lots of millions maybe of interactions like that. And that is different than another type of force, which is similar to what we see with ionic compounds, is if you just took one individual water molecule, the covalent bond and the sharing of electrons here between the oxygen and the hydrogen on each side, that's what's known as an intramolecular force. And an intramolecular force is the force that holds one single molecule together. So that's going to be like your covalent bonding, your sharing of electrons, and stuff like that. And the intramolecular force is always stronger than the intermolecular force. And we know that with water being our example here, because if we take liquid water and we heat it and we get to about 100 degrees, what happens is actually the bond between the different water molecules here, that's actually what breaks. And that's what allows this water molecule to go off into the gas phase and this water molecule at that point to go off into the gas phase. Now, if it was opposite and the individual bonds here, and each individual water molecule was weaker. When you would go heat something like water, it would all fall apart into like alphabet soup. You have like hydrogens coming off, hydrogen gas, oxygen gas coming off, and you obviously don't get that when you heat up water. It actually will just break the bond between different water molecules rather than the individual bonds in each water molecule. So intramolecular forces are always stronger than intermolecular forces. Hydrogen bonding, as we'll talk about in a later chapter, is actually a relatively strong sort of intermolecular force. And that's why water has a boiling point of 100 degrees Celsius. Now, when we think of something like methane, for example, methane is actually nonpolar. And the way a methane molecule and another methane molecule basically interact with each other is through a very weak intermolecular force. And that's known as dispersion forces. And dispersion forces is probably the weakest sort of interaction you could have between molecules. It is like a temporary interaction between these guys. So that is why, for example, something like methane, it's usually found as a gas because it is not held together. All the methane molecules, they're not held together by very strong interactions between the different molecules. You just look at it wrong and basically it will go into the gas phase. A lot of organic molecules are like that because they're nonpolar. If you think about sort of the first several organic molecules like methane, propane, butane, those are all sort of gases. And that's because, again, they're not held together molecule to molecule by very strong interactions. They're held together by these really weak interactions. So you don't have to convince it very hard for it to go into the gas phase. That's also why a lot of organic molecules are what are referred to as being volatile, that even though they may be in a liquid state, they can very easily just go into the gas state almost by themselves without a lot of convincing. And that's why typically if you use an organic compounds or you take organic chemistry, they usually put you in a fume hood because you do all the work inside there because that can happen very commonly. And a lot of those things are also very flammable, which is not good if you got flames out as well. So um, the general rule, as it says there, the stronger the attraction between one molecule and another molecule that's the same, the less likely it would exist as a gas under normal conditions. Kind of the weaker the interaction between one molecule and the next, the greater the opportunity that it will basically be in the gas state. So some substances that do exist as gases under sort of normal conditions, we have a lot of those diatomic molecules we talked about that are elements. So our hydrogen, nitrogen, fluorine, chlorine. Remember these guys again naturally come as twos, right? We also have O3, which is ozone. That is a gas under normal conditions. And then, of course, group number 8 on the periodic table, which are noble gases. So those guys, like our argon, neon, krypton, all the ons there in group 8. Those are the monoatomic gases, so they actually do come as ones and not twos, like our kind of diatomic molecules there. So here on the periodic table, again, these are normal conditions. You would expect these sort of elements to come as gases or be in the gas state. Also, a good point to talk about the difference between a gas and a vapor. A gas is usually referred to or used to refer to a substance that is normally in the gas state under normal conditions. Now, a vapor is something that is normally not in the gas state under normal conditions, but can be converted into a gas. So, back to the sort of example, water. When we refer to a lot of times water that is in the gas state, we usually refer to it as being water vapor. And again, that is sort of a substance that normally would be found a lot of times in the liquid state, but can be converted into the gas state. We usually don't call it water gas, right? So it kind of sounds weird. So we refer to it as water vapor. And again, vapor is usually used to a terminology that is used when something is not normally in the gas state, but has been converted into the gas state. Any questions on that there? All right, so let's talk a little bit about pressure of gases. And we do live at the bottom of the ocean. Remember, air is roughly 98% nitrogen, is actually the major component of air. Oxygen is next, followed by other gases, depending on where you're at, argon, carbon dioxide. The density of air decreases very rapidly with increasing distance from Earth. And as you go above sea level, the pressure starts to drop a lot, which is again why they would probably pressurize planes as you go on there. One of the obviously important properties of gases that we look at is pressure. And as we talked about, really what affects sort of the pressure either rising or lowering is the number of collisions that occur. And again, as these gas molecules are flying around, they obviously have a good amount of energy and they're going to start colliding, for example, with the walls of the container. And that is going to cause the pressure that we associate with gases. Now, one of the ways that we do measure pressure is we use a barometer. And old school barometers, which we don't usually have in labs anymore because they did contain mercury. But an old school barometer is basically a pool of mercury. And in that pool, you have sort of a glass tube. And as the atmospheric pressure sort of hits the pool of mercury, the mercury in the tube will rise. And mercury is one of those weird sort of elements, if you will. It actually will make a reverse meniscus in there. If that is actually mercury, it will actually go upwards. And you would technically read in this sort of reverse meniscus from the top of the meniscus if you were reading a traditional barometer. Like I said before, we don't have it in lab anymore. And a lot of schools have taken it out because it did contain mercury, the barometers and stuff like that. Um, a couple, kind of the big three, I would say, in terms of units of pressure that we really come across is an ATM, which is an atmosphere, a torr, and an mmHg. mmHg is actually millimeters of mercury, and that is because on this glass tube, in a traditional barometer, there was frankly a ruler. So there was a ruler on the side of the tube, and you would read it. Very commonly, you would read it in inches of mercury, centimeters of mercury, or millimeters of mercury. So you would read it like a ruler, how tall the mercury is in the tube, and that's where that name comes from. Torr comes from the guy who invented the barometer there, Torricelli. So that unit is where that comes from as well. And that is a one-to-one relationship. So one torr is 1 millimeter of mercury. So the good news on that conversion is you just need to change the units. It's basically the number stays the same. It's a 1-to-1 conversion. 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. Definitely need to know, right? Those. And that means 760 is an important number. It is our number that allows us to do conversions. So if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by 760. And you could either do millimeters of mercury or you could do torr, and that is an atmosphere. And if you do that, you will end up with millimeters of mercury or torr. And obviously, if you have millimeters of mercury or torr, and you want atmospheres, you're going to divide by the 760. And that will leave you atmospheres. So that 760 number, again, is a conversion. And I would say that out of all the units that we see, these are, I would say, probably the big 3 units that pretty much pop up a lot in chemistry: the millimeters of mercury, the torr, and the atmosphere. There definitely are some other units that we'll see here, I think, on the next page. But we don't really come across it all that much in chemistry. But here is a nicer picture of barometer again. Atmospheric pressure, barometer rising here, mercury rising. And again, you basically could take a reading here off of the tube like a ruler. Here are some other units. And like I said before, we don't really come across too much of these, but 1 atmosphere is equal to 101,325 pascals, or 101.3 kilopascals. Sometimes physics would probably use these guys. Also, when you fill up your tire in your car, pounds per square inch. PSI, 14.7 PSI is equal to 1 atmosphere, and 1.01 bar is equal to 1 atmosphere. That again is a very common unit as well. So I would say on this page, probably just these down here, you probably should know. This probably won't come across too much here in chemistry, but the bottom ones can pop up a lot, especially in book problems, stuff like that about PSI. And bar, I don't know how much bar you might see, but it's a good one. It's almost equal to an atmosphere. It's 1.01 bar is equal to 1 atmosphere. But again, the big 3 most common ones are those ones from the previous slide there, definitely. So let's talk a little about some gas laws. And when we talk about gas laws, there's really 3 sort of variables that we deal with, which is pressure, volume, or temperature. And in some gas laws, we may only be looking at 2 of the 3, and the other one is held constant. So the first gas law we're going to talk about is Boyles Law. And Boyle studied actually the pressure volume relationship. So he looked at pressure and volume. He kept actually temperature constant in this case. So Boyle looked at different sort of pressure volume relationships for gases. He kept temperature constant. And what he found was that a fixed amount of gas at constant temperature was inversely proportional to the gas pressure. So what he saw was basically as the pressure went up, the volume went down. And if you think about it, if you have a small volume and your gas molecules are in the small volume, they really don't have a long way to fly around to make collisions. So because of the small volume here, we would expect the number of collisions to increase, and that is why we would expect the pressure to also increase as well, because we're definitely going to have a lot more collisions occurring. Now, the opposite is true. The pressure will go down as the volume goes up. And again, if you just kind of think about it, give everybody a little bit more space to fly around in. Now these gas molecules will have to go a little bit longer of a distance to cause collisions. And that means the number of collisions overall will start to decrease. And because the collisions start to decrease, we will see the pressure also go down as well. So basically opposite relationship here. As pressure goes up, volume goes down, and vice versa. Give everybody a little bit more room to fly around in. We're going to actually start to see the pressure come down because the number of collisions are going to come down. There was an interesting sort of relationship that happens with Boyle's Law. And what he found was that if you took a bunch of pressure and volume measurements for a gas over time, it doesn't really matter how many you did, but you did a bunch of different pressure volume measurements. If you took the pressure times the volume for each of those measurements individually and times them together, it would always end up with the same number, a constant number. And that is what the little k stands for here, is what is known as a proportionality constant. And that basically means that, again, any sort of pressure and volume measurement that came together, if you multiply them, they will basically always equal the same numbers, regardless of the pressure and volume numbers that you are using in this relationship. Now, because of that, what that allows us to do in a situation like this is, because when you take P times V, it always equals the same number, you could actually set two conditions together. And if we set both of these conditions together, this gives us really Boyle's law as we sort of know it, which is P1 times V1 equals P2 times V2. This again is at constant temperature. Now, in terms of the pressure, it could really be any unit you want as long as they are both the same on both sides. So they do need to be the same units. And for volume, same deal. It could be really the same units on both sides. So it doesn't really matter. The units here, they don't have to be a specific unit for pressure or a specific unit for volume. But if you have two pressures or two volumes, they do need to be in the same unit for everything to cancel out correctly. So you can't have one, for example, in liters and one in milliliters. They won't cancel out correctly, the volume. It doesn't matter which one you convert them to. You can convert them both to milliliters, you can convert them both to liters, but you do have to make sure they are in the same unit. Same thing with the pressure there. And again, the relationship that we just talked about, pressure goes up, volume goes down, pressure goes down, volume goes up in this case. Any questions on that there? All right, so let's take a look maybe at a graph here, and this is Boyle's Law graph form. We see a much bigger volume, a lot more room for everybody to move around in, a much smaller pressure. And as the volume gets smaller, we see a much larger or higher pressure occurring again, because we're going to have a lot more collisions occurring in that particular case. All right, so why don't you take a moment here, and we have an inflated balloon, has a volume of 0.55 liters at sea level, which is 1 atmosphere, rises to 6.5 kilometers, where the pressure is 0.4 atmospheres. Assuming temperature is constant, what is the final volume of the balloon? So why don't you give it a go, see what you come up with. Okay, so let's take a look. So definitely, when you're dealing with gas law problems, it's a really good idea just to kind of pull out the information, maybe label what type of information it is. A lot of times that can kind of point you to the right gas law. Obviously, at this point, we only have one that we've talked about so far. But here, if we go through, that is obviously a volume, which is 0.55 liters. 1 atmosphere here is a pressure. 6.5 kilometers is useless, and we have another pressure of 0.4 atmospheres, and we are looking for a volume. So again, by just kind of pulling out the information, it really should point you in the direction of Boyle's law. Doesn't matter which ones you call ones and twos, the answer is no, as long as you kind of keep the numbers that go together. Most people just kind of go like how it's written in the problem. So these would be ones, these would be twos. So in this case, we're going to go P1 V1 equals P2 V2. We have all this information. We are looking for V2. We're going to divide that to the other side, and that will get us V2 is equal to P1 V1 P2. And putting in our numbers here, we will get 1 atmosphere, 0.55 liters, divided by 0.4 atmospheres. The atmospheres will cancel. In this case, our volume will end up being liters. And that's going to get us here basically 0.55 divided by 0.4, going to get us a 1.4 liters in this particular case. Any questions on the calculation? Now, because this is Boyle's Law, we could kind of make sure that perhaps our answers sort of make sense because the pressure here went from 1 atmosphere to zero point 0.4. So our pressure went down, which means our volume should go up. And it started at 0.55 and ended at 1.4. So it did go up, which is good. Again, it's a good thing to maybe think about because sometimes people have a tendency sometimes to inverse numbers or reverse numbers when they're rearranging equations. So again, if you kind of went down in this case in terms of your volume, that really shouldn't make sense based on the relationships that should happen here. Any questions on that there? Oh. That was the same one, I think. Yep. All right, the next couple of gas laws we're going to talk about is Charles' Law and Guy-Lussac's Law. And they sort of deal with a couple different things. Charles' Law dealt with volume and temperature, and it kept pressure constant. And Guy-Lussac's Law dealt with kind of pressure and temperature and kept volume constant. Now, if we think about sort of what's going to happen in these situations, we'll take this one first here. So if we have a container of gas and the volume is constant, which means there's no movable piston in there, it is what it is in terms of its volume. If I increase the temperature by maybe heating it up, we would expect our gas molecules to start to gain a lot more energy because you're obviously adding energy as you increase the temperature. That means our gas molecules here are going to start to fly around a lot faster. And because they're going to be flying around a lot faster because they have a lot more energy, that is definitely going to increase the number of collisions that are going to occur because they are moving around faster. And the collisions will go up, and we would see the pressure also go up as a result of that. So again, more temperature, more energy, faster moving gas molecules, more collisions, more pressure. Opposite is sort of true as well, which is if you have, again, some gas molecules here in a fixed volume, and you decide to decrease the temperature. When you decrease the temperature, our gas molecules are going to lose energy, and they're not going to fly around as fast, which means dramatically slowly drawn here. They're going to fly around a lot slower. And as they fly around a lot slower, that is going to lead to less collisions occurring. And because there's going to be less collisions, we will actually start to see the pressure start to go down in this case. So the relationship that we see here with constant volume is as you increase the temperature, just going to cause a lot more collisions and a lot more pressure because they're moving around faster, and vice versa. As you lower the temperature, they're not going to be moving around as fast. There's going to be less collisions, and the pressure will start to come down. Now, if we look at what happens here in Charles' Law situation, let's say we take that same container, but we have kind of a movable sort of piston in there that can change the volume. And if we have our gas molecules here and I decide to increase the temperature, we again are going to start to see the gas molecules move around a lot faster. Now, because they're moving around a lot faster, they're definitely going to cause a lot more collisions if the volume stays the same, and that's what happened over here. But what happens in Charles' Law situation is we don't want the pressure to change. We want to keep the pressure constant. So if we don't do anything with the volume, we will not have our pressure remain constant. So what happens in this case is we will end up with a larger volume. And what that will do is, even though those gas molecules are moving around a lot faster, they have a lot longer now distance to go to collide and cause collisions. And what that does is, by giving them a little bit more room to fly around in, it keeps the number of collisions relatively constant. And because it keeps the relatively constant the number of collisions, it will also keep the pressure relatively constant as well. And we will see that pressure remain constant. So in Charles' law, if you increase the temperature, the way it's able to keep the pressure constant is, in this case, the volume will get larger to keep the number of collisions the same, and that keeps the pressure the same. Opposite is true if you are in this situation and you lower the temperature. Again, just like we talked about over here, if you lower the temperature and the volume remains the same, you're going to start to see the pressure start to drop because the number of collisions is going to go down. So in order to keep the collisions from decreasing, the volume actually starts to, and I'll dramatically draw it here smaller, the volume starts to decrease in this case. And now, by kind of squishing everybody together and giving the gas molecules a smaller volume to fly around in, even though they are moving slower, it will still keep the number of collisions pretty much the same. And that is what keeps the constant pressure occurring here. So in Charles' law, because we really want to keep the pressure constant, it is actually the volume that adjusts to allow the collisions to remain the same and to keep the pressure constant. So as the temperature goes up, the volume goes up, and as the temperature goes down, the volume goes down here. Any questions on that there? Now, we'll come back to that slide in just a second, but if you kind of do a graph of volume versus temperature, which is our Charles law relationship, and you take any gas you like, so here we have helium, methane, water, vapor, hydrogen gas, and so forth, dihydrogen monoxide, and you sort of make a graph of volume versus temperature, and you extend the straight line all the way down to the temperature axis here, it will hit in the exact same location for all the gases. And we also see our Charles law relationship here: high temperature, large volume, low temperature at that point, smaller volume. But more importantly, for gas laws, this relationship here is really important. It will always hit at the same temperature, and that temperature is minus 273.15 degrees Celsius. And that number should look familiar to you because that is the number we use to convert to Kelvin. And Kelvin is the one that recognizes this relationship, because if we add 273.15 to that to convert it to Kelvin, we get 0 Kelvin, which is absolute zero. And that is what is known, obviously, as absolute zero, or the Kelvin scale. So, because Kelvin understood this relationship, or discovered sort of this relationship, what that means is pretty much a safe bet that if you are doing any type of gas law using any type of gas formula, the temperature always needs to be in Kelvin. So that's almost like an automatic thing that you should just always know and do when you're doing gas laws. You have a temperature, it needs to be in Kelvin. So, like obviously here, we're going to add 273.15 to our Celsius to convert it to Kelvin. Now, it is important that you do convert the temperature to Kelvin to get the correct answer. And what I mean by that is, sometimes people think they're given a problem where they have temperature given to them in Celsius, and they're asked to find a temperature in Celsius. So it does make sort of logical sense that if they kind of give it to me in Celsius and I need to give the answer in Celsius, can I just leave it in Celsius? And the answer is no, you cannot. You will get the wrong answer. So if you have a problem like this, you need to take it from Celsius to Kelvin. You need to then go into the gas law in Kelvin and then convert it from Kelvin back to degrees Celsius. So you do have to, whenever it goes into the gas law, even if the question gives you the temperature in Celsius and asks you For the answer in Celsius, you do have to convert it to Kelvin to put it into the gas law to get the correct answer. So, like I said before, it should be just like an automatic, like you see temperature, gas law. I'm just going to add my 273.15 to it and kind of move on. So, for sure, you should always do that. Any questions on that there? Yeah. All right. So we do see the same sort of relationship in these laws, and then these are our couple of gas laws here. So we have our V1 over T1 is equal to V2 over T2. This is Charles' law. And again, as we just talked about, our temperature here does need to be in Kelvin. The volume does not matter. So again, it can be any volume unit you want as long as they are the same on both sides. So again, you can't kind of mix liters and milliliters. You got to kind of choose. But for sure, temperature does need to be in Kelvin for it to work out correctly. And again, this is what we just saw in the previous slide, our relationship of as the volume goes up, so does the temperature. As the volume goes down, so does the temperature. Over here is Lussac's law, typically. And this also is pressure P1 over T1 equals P2 over T2. Again, does need to be in Kelvin. And same thing with our pressure. It doesn't matter the units as long as they're the same on both sides. And again, our relationship we saw here, pressure goes up, temperature goes up, and pressure goes down, temperature goes down. This again is at constant volume. This is at constant pressure. Any questions on those? So also a reminder that if you have issues rearranging equations, when you have any type of equation like this or the previous one as well, and there's an equal sign, for example, if you need to move something to the other side, it always ends up in the opposite location. So if I wanted to solve for V2, I would need to move T2 to the other side. It's on the bottom, so it'll end up on top. You'll end up with V1, T2, T1 equals V2. So again, that's sort of a quick way. You could kind of rearrange some of these equations. If you move it across the equal sign, it should end up in the opposite location on the other side. So if it was on the bottom, it should end up on top. If it was on top, it should end up on the bottom, and so forth. So it's a quick way to kind of rearrange those guys. All right, so I want you to try one here. In the experiment, we have 452 milliliters of a gas. It's heated from 22 degrees Celsius to 180. Okay, so let's take a look again. If we kind of pull out the information, we definitely have a volume here at 452. Temperature goes from 22 degrees to another at 187. And we are looking for a volume here. So again, if you kind of think about the formulas that we have, should really eliminate these since there's no pressures and obviously point you to our Charles law here. Again, we could call these guys ones and these guys twos, and we will use V1 T1 equals V2 T2. Automatic again should be temperature. That is definitely need to be converted to Kelvin. So we'll add our 273.15 for each of those and convert them. That's going to get us here 22 plus 273.15. Going to get us a 295.15 Kelvin and a 187 plus a 273.15. Going to give us 460.15 Kelvin. Once again, here our volume's okay. It just means that when we do the answer, we'll end up in milliliters. We are looking for V2. So again, just going to move this to the opposite location. That is the same thing as multiplying the T2 to the other side. V1 T2 T1 equals V2. Remember, whatever you're solving for needs to be up on top by itself, not on the bottom though. So putting in our numbers here, that would be V1, which is 452 milliliters, our T2 of 460.15, divided by our T1 of 295.15. The kelvins are going to cancel, going to leave us milliliters. And we will end up with here, looks like about 704, actually 705, we'll round up, milliliters here. Once again, this is Charles' law. And what we see in terms of our temperature is our temperature went down. It went from 22 to 187. And if the temperature went down here, I'm sorry, it did not. I'll go the wrong way. The temperature went up, 22 to 187. Temperature went up, the volume should go up. Yeah, 22 is smaller, I know. And that's what we do see here. The volume went from 452 to 700 milliliters. So it does make sense if you know how to count numbers, I guess. Question on that one there. All right, let's take a look at that's what we just did. Take a look at another gas law, and this gas law is our friend Avogadro, and he had a number, but he also has a gas law as well. And when we think about Avogadro's number, we should think about moles. And in gas laws, moles is equal to N. And his gas law involves moles. It actually involves volume and moles. Actually, keeping here, we're going to keep pressure and temperature constant. So on this particular deal, we're going to keep actually two things constant, temperature and pressure. And the volume of a gas is sort of proportional to the moles. So as the volume increases, so does the moles. And we have Avogadro's law here, V1 over N1 equals V2 over N2. And again, the N's here are moles of the gases, and obviously these are volumes here as well. Now, one of the relationships that comes from Avogadro's law is actually one that you can use in a stoichiometry type situation. You can obviously as well just plug and chug into Avogadro's law like any of the other gas laws there. And if you have some volumes and moles, you can figure out the other moles. But one of the relationships that is helpful from Avogadro's law is the idea that, as we see here, we have one volume is equal to 1 mole, 2 volumes gives us 2 moles, 3 volumes gives us 3 moles. So we do see this sort of relationship between the volume and the moles. And that's really helpful if you happen, for example, if we take a look at a reaction like this, and they're all gases, and this reaction is happening under constant temperature and pressure, we could actually do stoichiometry with uh, volume rather than moles. And why that may be a benefit is later on we're going to talk about doing stoichiometry involving gases. If you're under these sort of constant temperature and pressure conditions, it can allow you to shortcut using any type of gas law. So sometimes it's really helpful. You don't have to use a gas law. So how does this work? Normally, if we were to look at the stoichiometry of this equation, we would use the mole-to-mole relationship, and we would say 1 mole of nitrogen reacts with 3 moles of H2. 1 mole of nitrogen gives us 2 moles of NH3, and we would say 3 moles of H2 gives us 2 moles of NH3. Now, because these are all gases and we're at this constant temperature and pressure conditions, this falls underneath Avogadro's law conditions. And we could go through this and actually not use moles, but basically just use a volume. So for example, we could say for every 1 liter of N2, we would get 3 liters of H2. We could also say for every 1 liter of N2, we would produce 2 liters of NH3. And lastly, we could say for every 3 liters of H2, we get basically 2 volumes or 2 liters of NH3. So we could use this relationship for stoichiometry. So for example, if we started with 6 liters of H2, and we wanted to know how many liters of NH3 would we produce, we could actually just use stoichiometry with liters to liters conversion that we could get just like we do mole to mole. So we could take our 6 liters of H2, go to the equation and look between H2 and NH3, and it would be this relationship here. And we would go 3 liters of H2 on the bottom, gives us 2 liters of NH3 up on top. And again, we're going to end up here with 4 liters of NH3 would be produced in this case. And this allows us to get to our answer. We don't have to actually stick it into any type of gas law or anything like that. And we can just kind of do a volume to volume relationship. So this is a thing that you should keep in the back of your mind in case you come across a stoichiometry problem that's gas, happens to be temperature and pressure constant. You can kind of just zoom right into the stoichiometry without having to worry about incorporating gas laws into the calculation. As we'll talk about later on, you could actually still do gas laws in the stoichiometry. You'll get the same answer, but there's a lot more steps to it. Um, this is a nice relationship that sort of comes from Avogadro's law. Any questions on that there? All right, so if we put together pretty much all of those previous gas laws, if we put together our Boyles, our Charles, our Avogadro's law, we get really the granddaddy of all gas laws here, which is the ideal gas law. And the ideal gas law is PV equals nRT. Now, this is different than the gas laws that we've seen previously. On the gas laws we've seen previously, there's kind of like a before and after. So 2 pressures, 2 volumes, maybe 2 temperatures. This is a one and done situation. There is no 2 pressures, no 2 volumes. It's just one of everything. It is also the most restrictive in terms of units. So if you are using the ideal gas law, 100% of the time, your pressure needs to be in atmospheres for everything to work out correctly. So if it's not, you need to do that conversion. For volume, it needs to be in liters. For moles, it should hopefully be in moles. For temperature, no surprise here, it does need to be in Kelvin. And the reason that all of those need to be kind of in those units is the value of R, which is the gas constant. R has a value of 0.08206, and it has units of liters times atmosphere divided by Kelvin times mole. So clearly, obviously, need to know, right? Along with all the formulas that we've been talking about as well. And the good news is if you remember the gas constant, the units that go with the gas constant, it tells you what everybody else in the ideal gas law has to be in anyways. So that's why everybody else has to be in these units for all these units to properly cancel out. So it can kind of help you. What is an ideal gas? An ideal gas is typically a gas that we normally deal with under normal conditions. And there's really kind of 2 things that make something an ideal gas. One thing is that if we have a ideal gas, the volume of the gas itself is not important compared to the container volume it is in. So if you think about a lot of problems that you come across in gas law chapters, a lot of times they don't really talk about the volume of the gas itself. They'll oftentimes talk about the container has this volume, or the gases are in a 2-liter vessel or something like that. So a lot of times they will talk about the volume of the container itself rather than the volume of a gas, the gas itself. And that's because under ideal conditions, which is our normal sort of conditions, um, the volume of the gas is so small compared to the volume it's flying around in the actual volume of the container is more important, because one of the things we talk about gases is it will fill the container uniformly as it's flying around in it. So it will have a volume equal to the container because it can basically fly around in the entire container. The other thing that makes something an ideal gas is there is no interaction between gas molecules. So what I mean by that is if you have a bunch of different gases, for example, flying around in a container, they will have no effect on each other. So even though they technically are in the same container, even though they're flying around in the same sort of space, if you will, because we assume ideal conditions, it is almost like, for example, gas A in this example here is in there by itself. Gas B is in there by itself. Gas C is in there by itself. There will be no attraction or repulsion between different gas molecules. So the gas molecules, even though they're flying around in the same container, will not be attracted nor repulsed by any other gases there. And those are the two main things that make something an ideal gas. Something we'll touch upon in this chapter, not really go into great detail, but if you go and take 1A, you will go into great detail. There are gases that are considered real gases or non-ideal gases. And those gases, you do have to take actually those two things into account. And that happens at really high pressures and small volumes is really when that comes into play. But even under normal conditions of pressures and temperatures, under sort of room conditions and things like that, gases fairly behave ideally. You have to get super high in the pressure and really kind of super low in the sort of temperature and volume there for that real gas to sort of come into play. Now, a couple of important relationships that we have here with gases is, we'll start with this one here, which is STP. STP stands for standard temperature and pressure. So if you're given a problem and it says it's at STP, it is actually giving you two values. The pressure value would be 1 atmosphere or its equivalent, and the temperature would be 273.15 Kelvin. So if you come across a problem that says, what is the volume at STP, those are the two values that you could use for temperature and pressure, 1 atmosphere and 273.15 Kelvin there for our temperature. Now, there is a good relationship that occurs if you happen to be at STP. So if you happen to be at STP, 1 mole of any gas will equal 22.414 liters. So this is a conversion that you could use if you are at STP. That would mean that the temperature does need to be 273.15 and the pressure has to be 1 atmosphere. What will that allow you to do? That will allow you to do, in some cases, not have to use the ideal gas law. So you could just kind of use that relationship. You could kind of avoid using the ideal gas law if you're at STP conditions. If you are not at STP conditions, you should never use that conversion. So that conversion is specific for STP conditions. If you're afraid that maybe you might use this conversion in the wrong place, you don't even have to worry about remembering that conversion. Just put it into the ideal gas law and use the temperature at 273.15, use the pressure at 1 atmosphere, and just solve for whatever you need to solve for. So the nice thing about the ideal gas law is it's kind of a universal gas law. It pretty much works in any conditions and with any gas. So it's not specific for a gas. It's really not specific for a condition other than it does need to be ideal conditions, which is normal conditions, to use it. By the way, if we do take the ideal gas law and solve for R will equal PV over NT. If we put in our values, pressure 1 atmosphere, 22.414 liters, 1 mole, and our 273, that is where we get the value of the gas constant from, that 0.08206 number. So I personally, like I said on the previous slide there, I use 0.0206. Books and people nowadays do round it sometimes to 0.0821. So either one is fine, and you'll probably see either one. I personally do kind of use that most of the time because that's the one that's in my head. But nowadays, books and stuff like that, sometimes people will round a little bit to 0.0821. So, if you want to use that number, you pretty much should get the same answer along the way. Any questions on that there? All right, let's try this one. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas, then a volume of 5.43. Okay, let's take a look. So again, if we kind of pull out the information, we are looking for a pressure. We got moles, 1.82. We have a volume that's 5.43 liters and a temperature that's 69.5 degrees Celsius. So again, we only really have one of everything, so that clearly rules out all the other formulas. You could probably kind of see the ideal gas law is probably the right one there to choose. We just got to make sure everybody's in the proper units because remember, this one is pretty restrictive. A number that you always have available to you that is probably never given in a problem, again, is R. So that is a number that they just assume you know and is always available to you. Like I said, very rarely ever mentioned in a problem when you're doing it. Our moles are in moles, so that's good. Our volumes in liter, that's good. Our temperature does need to be converted, so we'll add our 273 to it, and we'll end up with 273.15 plus 69.5 gets us 342.65 Kelvin. So we now have pretty much everything we need. We have this, and this, and we're looking for this. It's not really a fraction, but you can think of it as being up on top, which means volume will end up on the bottom as you go that way. We're going to divide by the volume. Basically, P is going to equal nRT divided by V in this case. And that's going to put our numbers in here. So we will end up with our 1.82 moles, our 0.08206, which is our R value here, our 342.65 Kelvin, all divided by our volume here of 5.43 liters. In terms of units, the moles will cancel, the Kelvin will cancel, the liters will cancel. Going to leave us only atmospheres left from our R value. And if we put it in there, we'll end up with 1.82 times 0.08206 times 342.65 divided by 5.43. We are going to end up here 2.0826 times 342.65 divided by 5.43. That looks more like it. All right, 9.42 atmospheres in this case would be our pressure. First off, any questions on the calculation? Now, in this particular problem, they did give us moles, but it is very common in these problems. You need to go from grams to moles. So again, that is our molar mass conversion. Grams per mole from the periodic table. That's a very common conversion. And I would say also very common in these type of problems in terms of conversions, the 1,000 milliliters is 1 liter, yeah? So going from milliliters to liters is a very common conversion as well. A lot of times you're given the volume in milliliters and has to convert it to liters before you go into here. So those two conversions also use, in addition to obviously like normal converting our temperature into Kelvin, is used a lot in these kind of guys here. Any questions on that there? All right, we're laid up there for today.